Okay. All right. Recording's on. There you go. First of all, the announcement I want to make about tomorrow's lab. Tomorrow is lab number 2. And remember that you download your labs by going into the course information page on Blackboard, that link on the left. That's what I mean when I say a page or a section. That's all those things that are on the left. The orientation, course information, and then click down to where it says laboratory exercises. There's some old picture of people looking at a microscope, and click in there and download that. Okay, so that'll be the lab that we do tomorrow. Now, I've only done this lab once, so the caveat is that we might really do some science tomorrow, or is tomorrow? Yes. Oh, God, I'm getting confused about my mini masters here. So what I mean by that is I did it once in the previous semester and it worked out okay, but there were some things that didn't really work the way they should have, and we were able to hopefully make some corrections. But the nice thing about this is whenever we try these new labs, it gives us instructors and gives you all a chance to actually get engaged in the whole scientific method. It's so many times labs become cookbook. And what I mean by that is you go put A into B and voila, this happens. And it's the same thing. And it's good for the students, don't get me wrong, but there are also times that it's nice to be able to do the science. So when we're ever developing and honing and tweaking these new labs that we're trying, I think you'll like it too. It's an interactive thing with a computer too. Things don't always work out the way they are. So and I don't mind that in lab. I like talking about why things didn't come out the way they are, because it's kind of boring to always say 2 + 2 is 4. I like talking about when 2 + 2 is 5. Okay, so the big part of what we did in last lecture, of course, was go through each of these properties of water. And what I tried to do, what I tried to make the connection with y'all is I tried to take the physical or the physics or the chemistry behind what's happening. So, for example, the reason why water molecules are cohesive, right? The reason why they stick together. And I tried to turn that into something that is important for living organisms. In other words, how does this, the chemistry, how does the physics relate to the biology? There's something we always talk about, more so in anatomy and physiology, is that one of the things that we kind of teach you overall, again, especially in kind of an A&P course, is form and function. We'll do a little bit here, especially when we get into the cell and we talk about respiration and that sort of stuff. What I mean by form and function is how does something look and how does that translate into how it works? Now, if you're going on into A&P or anything like that, the first thing you'll learn about typically is going to be muscles and how they work. And you'll understand what I mean if you do take those courses, how the way a muscle is constructed is very uniquely evolved to be able to do the job, the function that it's doing. Now, the reason why I go off on that tangent, it's the same thing with water and talking about living things. I want you to understand not so much the form, but maybe the physics, right? The chemistry, the reason that it's hydrogen bonds and how that happens, right? How that holds water molecules together. And then again, I would want you to be able to tell me, well, okay, what does that do for living critters, right? It's how plants get water up against the force of gravity because, of course, water's got to fall down. Let me clear up the adhesion-cohesion thing the other day. I'm not sure I did a great job of explaining it, and I was thinking about it again, and there was, I think, one key point that I kind of missed that'll help you remember what is what. Adhesion is when two things stick together that aren't the same. So when the water molecules, because they're sticky, that's what it means to have poles, stick to the side of those conducting cells, not only are water molecules sticky, remember even ammonia has positive, negative ends. Okay, that's what I'm going to mean by sticky, like magnets are sticky, all right? But other molecules, remember even proteins will have stickiness to them, right? So water molecule can stick to that sticky thing. When it's cohesion, CO, co, all right, co refers to, like we talked about in covalent, but in this particular case, it means the same. So if you are cohesion, it's two water molecules sticking together. If a water molecule sticks to, excuse me, some molecule that makes up the cells of those water conducting cells inside of a tree, then it's adhesion, right? So the little spider walking down below on the surface tension of the water, then notice, isn't that so cool? Just barely pushing down on those water molecules. The reason why it doesn't fall, through is that due to cohesion or adhesion. Let's see if you can apply what I just told you about that. So which one of those explains why that spider does a blip fall through those that surface of water molecules? Cohesion or adhesion? Well, remember how I defined it again, right? Adhesion is when two things that aren't the same stick together. It could be water to the conducting cells. It could be substance A and substance B. As long as they're different, if they stick together, it's adhesion. Like Scotch tape is an adhesive, right? Because it'll stick to anything, stick to paper, stick to your skin. But now, how does that differ then from cohesion? And think again about the CO, what that little root means. You also see that root in other words like cooperative, and then kind of think about what that means. See, that's what I mean about kind of being what we call a wordsmith, looking at words and saying, wow, how can I remember adhesion versus cohesion? Does anybody else got can help Zach out? Is that spider able to walk on those water molecules because of a property called cohesion, or is it the property of adhesion? Okay, Tim, help Zach. Why is that cohesion? Why is, or in Italian, cohesio, right? No, why is that cohesion? Hi, Wyatt. I see that you came in, and Tim, I think I already said hello to you, but good morning. So you can jump in as well. Yeah, which bonds? Which bonds? You're right there, Tim. Which bonds? Okay, wow. The water molecules are alike, okay? So it's, there you go, Tim. You got it. The polar bonds of water molecules are holding the water molecules together. But Zach, the reason why that spider doesn't fall through is through something called surface tension, right? Water molecules stick together. They make hydrogen bonds. Excuse me, they're not very strong. I mean, you couldn't do this, obviously, so it's really a balance between weight and the way that the spider spreads out its legs. But those indentations are direct evidence of water molecules that are bending, right? Because those hydrogen bonds are flexible. Remember, they're kind of like springs, I told you, because that's how they can absorb so much heat. Those springs start bouncing. So those springs are stressed when the spider's standing on top of them, but not enough to break the springs, and the spider falls through. Now, it's cohesion because it's the water molecules sticking together that allow the spider to do that. The water molecules aren't sticking to something else. They're sticking together. The spider, she is taking advantage of the fact that that surface tension of water is really able to support a little tiny bit of weight. I looked online too. You gotta you can float needles, metal needles, sewing needles online. There you go. Yeah, thanks everybody. Perfect. Group effort. I love that stuff. Sometimes it's so beneficial for an instructor, a teacher, to have other students teach each other, because you remember, this stuff is second nature to me, and sometimes it's easy if you go, oh, and I learned things from y'all. I go, okay, that's a way to help connect too. So, all right, so cohesive water molecules help spiders float. Adhesion, now let me make sure you understand. Cohesion between water molecules, cohesion can occur between any two things that are the same. The co and the ad refers to, are they the same sticking together, right? Co, or is it one substance A sticking to substance B? All right. Where are we going? The fact that water is a really good radiator, right? I kind of went off into some specifics here about how we measure heat. That's basically what calories are. I told you that your food has calories because that's exactly what they do. They burn it up. They catch it on fire. What I call them, a bomb calorimeter. Remember that? And then the amount of heat that comes off is energy. Heat is energy, folks. We call it, in thermodynamics, we call it wasted energy, because energy is, well, if you think about it, you even know this if you've never taken a physics class, you need energy to do work, right? You need energy to do work. Now, we'll talk more about this in the later part of the semester when we talk about food and how that all works. But heat is a type of energy, but it's typically considered wasted energy. It's energy that's given off into the environment, okay? So that's what we're talking about in this situation about what are we measuring? We're measuring heat, which heat is energy. A Big Mac has more energy in it. Like if you burned it up in a bomb calorimeter, it would make a hotter fire than a Cheeto, right? One of the little Cheeto things, which I hate. My wife loves them. My God, those things are so gross. I don't think there's anything in them that's normal or natural. Okay, so if you got any questions about these definitions here, get back with me. But we went through those, all right? Water molecules are bouncy, so that's why they're able to absorb that heat. It makes Earth a good place to live. Mars, not so good. There ain't no water on Mars. And when the temperature goes down, remember what the oceans do. That's why it's so nice in San Diego. The warm oceans, warm because the sun has warmed them up. When the sun goes down, I can make a song out of that. When the sun goes down, then, of course, the warmth comes out of the water into the atmosphere. It makes San Diego a wonderful place to be. You don't get that because in Palm Springs, or you don't get that out there because that's a desert. And deserts, they have no water vapor. They have no blanket to keep the heat in, so the heat goes right out into space. That's why you can cool off. Remember I was telling you in my hometown, El Paso, people could go out in the middle of the desert and freeze to death. Okay, so we can cool off either by sweating, or this ingenious Thompson Gazelle has figured out this radiator in its nose by which it cools off its warm blood from its heart in its nose before it goes to its brain. Now, are all organs, the heart and all the other organs that blood might serve, are they affected by heat? Yeah, brain is affected first, okay? Brain starts shorting out, you're messed up. And one of the ways that brain starts shorting out is you getting too hot, okay? So you want to keep that brain cool. All of you were not impressed when I told you that ice floats, right? Until we kind of looked at it and said, right? There's a minute in there. Is my microphone working? It doesn't look like it is. Okay, all right, hello. It is, huh? Oh, sorry, guys. Geez, this new program. There's usually a little white indicator bar that bounces up and down, so I know if I'm getting too loud, but it's not working. Anyway, so y'all weren't impressed by ice floating until I told you, come on now, ice is a solid benzene in the right. That doesn't float. And we did that density thing in class. Solids, right, are typically, this is such a cool concept here, folks. It explains, again, why fish can stay alive when lakes freeze over. It can explain why orange grove farmers spray their crops and all that sort of stuff. But what's so neat about that is showing that Mother Nature loves curveballs, folks. She loves to make 99.9% of the time something like this always happen this way, but then she loves to throw those curveballs in there. Ice is one of those, right? It's solid. Typically solid, sink, and liquid. Solid, greater density, liquid, less density, gas, least density. It's a rule. Heavier or higher density items sink in lower density. Can't change that. Ice doesn't change that rule of physics. Ice chemically messes with that because when you freeze water, when you turn it solid, the hydrogen bonds, you remember we talked about what heat does to molecules? The more heat there is, it's energy, right? Molecules start bouncing around. If you look underneath the microscope, when we do the microscope lab, it's not in the labs. If one of you remembers, let me go get the India ink out of the back. You can put a little bit of India ink. India ink is little tiny pieces of carbon suspended in a liquid. You can put a little bit of, I'm getting excited here. You can put a little bit of India ink on a microscope slide, look underneath the microscope, and you can see the effect of molecules moving around, folks. You can't see the molecules, but you'll see those little black particles in the India ink, those carbon, they're bouncing, they're jittering. You're like, why are they jittering? They're jittering. They're jittering because molecules are bouncing off of them. Things you can't see are making that little particle that you can see bounce around at a very small level. Don't let me forget that, all right? But as it gets colder, that bouncing that occurs between molecules or even molecules and carbon particles in India ink slows down, less bouncy. Springs of the hydrogen hydrogen bond springs of the water molecules are springy, but they're getting colder and they're getting less springy. They're getting very close together, very non-spring, right? They're unsprung. And that's at about 4 degrees Celsius in water. Now that's still liquid. Here's the trick. Because of the hydrogen bonds, and it's the chemistry, all right, I didn't get into detail, but if you took a chemistry class, you'll learn precisely why. But because of hydrogen bonds, when you cool water off further, when you go 3, 2, 1, bingo, you're solid, right, at 0 degrees Celsius, the water molecules, the hydrogen bonds actually push each other apart a little bit. Just a little bit. That's because there's some rule, some chemical rule out there that says water molecules, when they're frozen, have to be about, remember that number down there, 4.48 angstroms? We measure like distances in molecules at angstroms. There's, I don't know, a bazillion, zillion angstroms in a meter. They're really small, okay? So they push back out again. So, of course, when they push back out, and they're further apart. Now, go back to density again. Solid objects, molecules are denser, they're closer. Gas objects, gaseous things, the water molecules are further apart, right? They're lighter, they float typically. Liquid molecules, they're in between. So what you've done is when you're cold and the molecules are closer together, you've pushed them a little bit apart and they float. Bing, bing, bing. Now, water's special in doing that. I'm sure there are other things out there that do that, but water is very special in doing that. And because of that special chemical property, all this happens, right? Not the husky walking on the air. Well, the ice floating or freezing at the top of the lake does. Lakes don't freeze solid through. They don't freeze in Florida at all, thank goodness. I always told my wife, if it snows, I'm moving to the equator, somewhere around the equator. I love to go skiing in snow. I don't like dealing with cold. But anyway, so all this is possible for us living critters because of hydrogen bonds, right? Because of that little trick. Are you starting to get what I said about at the beginning of the semester about how it's so fascinating to think how, walking on edge we kind of are as living creatures? I mean, it's a really incredibly delicate and complicated thing called life, physiology of life, right? All right, so enough of my soapbox right there. Water dissolves most things. We call it a universal solvent. Yeah, maybe there's some things human beings invented that it doesn't dissolve, but nonetheless, it dissolves things. And what we mean by dissolve, down there at the granular level, like you look at that salt crystal there, what we mean by dissolve is the water molecules, because they're sticky, and you know what? Ions are also sticky, aren't they? Remember, I'm saying sticky is equating with positives and negatives, because that's what positive and negatives do. Well, anyway, sticky things also stick to each other. So the water molecules come in based on, ranging themselves. So the positives and negatives are attracted to one another on those salt particles, and they pull them apart. Now you think, well, sodium and chlorine are attracted to one another. Who wins? All of them. It's like when the Native Americans would surround the cowboys, during the wagons, and they would shoot out and all that. I don't know if that really ever happened. Maybe it did. But anyway, if you get enough of those water molecules around, one water molecule couldn't do it. One water molecule can't do it, but maybe a bunch of them can. It reminds me of the way wild canines hunt. I think I was talking to you guys about earlier. It might have been my bio too. I'm fascinated. One of my hobbies is strategies. Like, I like reading books about military conflicts, not because people die, because the strategy. It's like I like your chess and that kind of stuff. I'm not very good at it. I suck at it, actually. But I like that sort of stuff. And so one of the things I like to do is find when animals have strategies. And wild canines, like African wild dogs, have these unique, it just blows me away. They get together and make up these plans. But anyway, I have no idea how I got there. But anyway, water molecules tear things apart, right? They dissolve things. And the versatility of water is the fact that it dissolves most things. Now, in your cells, we're going to talk about cells in a couple of chapters, there's all these parts, but most of your cell is liquid. Just like Earth is most liquid, most of your body is liquid, most of your cells are liquid. And the reason why that is liquid is the spiked punch of the high school dance. Okay, it's the social, that's a horrible example, but nonetheless, when I was a kid, right, it always seemed like it happened that way. And that was the social lubricant. Well, the teachers found out about it pretty early. But anyway, what we're saying, what water does is it gets everybody to mix. It gets everybody to mix. Everybody starts mixing. Everybody's moving around. And how does particle A get with particle B to do some chemical reaction in chemistry lab? You pour them together in a beaker. Okay, particle A is in this part here, particle B is in this beaker. I pour them together, and blah, something happens. You know, if you're in my 7th grade chemistry class, boom, flames came out, and the fire alarm went off and all this other wonderful stuff. Got out of school half a day earlier. In your cells, how does that happen? There ain't nobody in your cells with beakers going, mix these two things together like a mad scientist. A gets with B because they randomly, little jittering Indian ink particles, those molecules are randomly bouncing off each other. Molecules randomly bump into, hey, I know you, you're B, I'm A, let's make C. That's how they do it, they randomly. And if you can do a few things to increase the odds of them randomly bumping into each other, make a lot of them, okay? Cram a few 100,000 in that cell, warm them up, because they're gonna move faster, okay? And what was the third one? Was there a third one? Put a lot of them, warm them up, and whatever, anyway. So you get the idea? Oh, put them in water. My whole point here, holy cow. Put them in water because everything dissolves. Everything starts moving around. Everything's cool. Everything's loose with water. Okay? Hydration shells. Since ions are sticky, they do. It's like the Native Americans surrounding the cowboys. They surround, well, the settlers, let's say, couldn't necessarily have been cowboys. They surround those particles. They surround those ions. Hey, for a blast from the past and a little bit of a review, the positively charged ion, the sodium, what's the official name for a positively charged ion? So we would say sodium is the what? And chlorine in this is, there you go. And what's the other one? Anion. There we go. Anion. You should think of some way to remember that. I don't have a particular way. I just kind of do remember it. But if you're getting it back and forth, one of the ways you remember is the word cation is Ca, so plus minus maybe. So the cation and the anion. I don't know. If you're having troubles with those, some of those things always confuse me. Like what's the one? I can't remember right now. See, all right. So large proteins. Not all molecules stick to water, right? Because we learned at the very end of class, we'll get to that next slide, that there's hydrophilic and hydrophobic, right? But that doesn't mean that not all parts of all molecules are that way. Proteins, that big purple thing, are huge. We're going to talk about proteins later on. They're these massive molecules. So water molecules, because they're everywhere, right? Those protein molecules in your cell, the water molecules surrounded it, and they're picking at it. Oh, where can I start pulling things apart? Where can I do my universal solvent thing? They start, can't do here. Oh, wait, here's a sticky part. And why is it sticky? Because somewhere in that proteins, when we start talking about how proteins are made, chemically, there's a sticky area. And the water goes, ooh, here, guys, pull on this, pull, and they start pulling things apart. Okay? See how that works? That's what dissolving is. Dissolving is the solute, that which gets dissolved, the salt in the salt water, is being torn apart by the solvent. That's why oil does not dissolve in water, does it? Right? You never hear anybody say that. If they said it, you would now correct them, wouldn't you? Does oil dissolve in water? Beth and Lindsay, yeah, I think one of you actually said the word last time in class about what is that the word? No, it was emulsify. What is multiply? Is that a word? Did you just make that up? Oh. Okay, because I was trying to look it up going, I don't want to be done. Emulsify, that's all right. Yeah. And remember, emulsification takes fats and makes them in little tiny particles, oils. Yeah, I'll slow down so you guys don't have to type so fast, but still. Yeah, that's why we say all the dispersant that BP put in the Gulf. Oh, it went away. No, it didn't. It's like saying, if you tore something down to its smaller and smaller parts, when it became molecules, it went away because you can't see it. Well, that's what that dispersant does. It emulsifies. Emulsify means just that. It doesn't dissolve. It just separates into little tiny particles. Each of those little tiny droplets. God, no. especially the birds. It's the worst thing. Yeah, the only dishwashing detergent that works, of course, they love it, is Dawn. You notice in all those, yeah, Dawn is unique in the terms of its formulation, that it cleans off the oil without damaging their skin or irritating them. I'm sure they don't. I'm sure Dawn doesn't mind that. Okay, any questions on this terminology here? We all know that oil and water doesn't mix, but y'all remember what I mean by hydrophilic? Well, Lysol is disinfectant, right? So it's probably got some sort of a disinfectant solution. It's probably got alcohol in it, which helps. Alcohol is a good general thing. It tends to dry things out. But you have to look at the ingredients. But my guess is probably got some other chemicals that when you spray it on stuff is really bad for the bacteria. And then as it accumulates, it ends up being bad for you, maybe. I don't know. But yeah, no, Lysol's been around a while. It's funny sometimes you look at these things. Now it got me curious. What is Lysol made of? What is Lysol? Because it smells good anyway. Holy cow. Yay. The active ingredient is benzalkonium chloride. I'll bet that's some sort of an antibiotic or anti-something or other. Let's see what that is. It's a cannatopic surfactant. Oh. Okay, surfactant. Oh, good. A surfactant. What the hell word is he saying? Does anybody know what that is? Yeah. Soap is a surfactant. If I wanted to make it wouldn't want to do this to the spider, but that spider walking on the water, if I wanted to make him fall through, I could do it very easily. 1 drop of soap nearby. Just put 1 drop of soap onto that surface of water, and what surfactants do is they dissolve things, they break things apart. So that 1 drop of soap would separate those hydrogen bonds between the water molecules, and the spider would fall through. Water softeners are usually things that precipitate out. In other words, remove the minerals that are in water, right? They just basically physically engages in a chemical reaction by which those minerals are removed or they're broken down. Soaps, like I said, soap like Tide and Amphiphile, the hydrophilic part is attached to the oil, the hydrophobic part to the water. And when it leaves your washing machine, which reminds me I have sheets anyway, they're being connected, drags everything along with you, like it does to oil in the commercial. Yeah, like it spreads it apart, it beads it up. Yeah, they say, oh look, it's dissolving, or I don't know if they use the word dissolving, but now you know what it's doing. It's emulsifying, and soap is the surfactant. So that stuff in Lysol is a surfactant. So what it does, it destroys. In this case, it says here, lipid, increasing drug penetrate. Okay, so what it does is it destroys the fat, the lipid layer on the outside of bacteria, so that the drug, whatever's contained in it, can destroy the bacteria. That's what it says, from what I can see. Huh, good question. Lime and calcium and stuff in the pan. Wait, that's 2 you get, like it does the oil conversion. Oh, in the pan. What removes lime and calcium? Tim, which one? Yeah, it does. No kidding. Yeah, vinegar, acids will do that. Yeah, acids will help dissolve some of that. Although sometimes you need a really strong acid. Yeah, I figured that. Actually, I think there is a bug called a vinegaroon that is spelled with an A, though. So you're not so far if we're talking about a bug. Okay. All right. Now here, next, this is a new slide. Moles. There's a mole. Want to hear a joke about moles? So 3 moles are walking home, and they're burrowers. So they're walking home in a tunnel, 1 mole behind the other, obviously. And as they get closer to their home, the first mole sniffs up because they got pretty good noses. They're not have very good sight. They don't need it. They live on the ground. Eyes are expensive, so if you don't need them evolutionary, get rid of them. Make that nose something. He sniffs up. Oh, we're having roast beef for dinner. So the second mole sniffs up and he goes, no, I think that's pork chop. It smells like pork chops. The third mole, of course, he's in the back end of the burrow. He goes, I just smell molasses. Early in the morning, I know. We're not talking about the mammalian mole here, even though they are kind of critters. We're talking about what a mole is when we talk about thank you. When we talk about chemistry here. So let's define what a mole is, all right? You may not have ever heard it before. You may not ever see it again, but if you take a chemistry class, you might. And it looks a lot more difficult than what it really is. Okay, let me give you the definition first. Some guy named Avogadro, I was looking him up online. He was kind of an interesting dude here. What did he say about Avogadro? Did I already get off of it? Yes, too far. Wait, hold on. He was a scientist, Emilio Avogadro. Anyway, he came up with this idea that of Avogadro's number. Now, Avogadro's number has a specific number. It's up above, 6.02 times 10 to the 23rd. Okay? It's a big number, isn't it? How would you turn that into a number without the times 10 to the 23rd? What would you do to the decimal place? How would you write that number out longhand? I'm not even going to bother because I lose count. There you go, right? And then you're going to move that decimal point to the end. So we're talking about a bunch of whatever, all right? So Avogadro's number says 1 mole, abbreviated MOL, 1 mole is that many molecules. It can also apply to substances. And sometimes when I've seen it online, it's a good way to explain it. A mole is that number of anything you define. If we want to define a mole of apples, we would say, well, we're talking about 6.02 times, we're talking about a boatload of apples, times 10 to the 23rd apples, okay? So that's what we mean when we say a mole. So a mole is 6.02 times 10 to the 23rd molecules. It can also refer to atoms. So I put that in there so you're not confused. A mole is the number. That big, long number is a mole, or whatever you're talking about. Okay, now, how do we use it in chemistry? Well, we use it in chemistry to help us answer a question about something called molecular mass, all right? So molecular mass is basically what the word says. It's looking at a substance and adding up all the atomic masses, all right? We talked about atomic mass, like, for example, with carbon. Carbon has atomic number 6. Okay, does anybody remember what the atomic mass of most carbon is, of your typical carbon? Remember, there are variants, there are isotopes of it, but what was your typical carbon? Tim, 14 would be the isotope. That's right, carbon 14, but yeah, Beth and Lindsay, carbon 12, right? So what is, without the electrons, because we ignore those for the most part, how much does one carbon atom weigh? Weighs 12, right? Weighs 12, Tim, because carbon's got 6 protons and they weigh 1. Carbon 12's got 6 neutrons, and then, like I said, we're ignoring the electrons. All right, so the number in the upper left is the atomic mass, taking all that into consideration. What you might get confused by is, like if I said, if you wanted to figure out the number of neutrons, you just simply divide the number of subtract the number of protons. That's what the 6 tells me. So 1 carbon atom weighs 12. Okay. What's the unit, folks? Whenever you give a number, like we talked about density in class, 12 watts, 12 pounds, 12 kilograms. What's the unit that we're talking about here? AMU, atomic mass units, or Daltons, right? Dalton, right? Okay, so that's the atomic mass. So here's how you do it. I'm going to show you an example. Let's look at glucose. There's the atomic formula, C6H12O6. Now again, excuse me, don't bother with memorizing atomic masses or atomic numbers, even atomic symbols. If for some reason by the time you took the exam you didn't recall that O was oxygen and you called me over on a question, I'd be more than happy to say, yes, that's oxygen. Okay, so don't worry about that. And if I asked you to do a question or a problem like this, I would give you the information you need that you see down below. I'd give you the masses. A carbon atom weighs 12, a hydrogen atom weighs 1, and an oxygen weighs 16 Daltons or AMUs. Everybody follow me so far? Any questions on any of that? Cool. All right, now we're going to solve for molecular mass. The molecular mass is the sum of all the atomic masses of all the atoms, okay? Not just of one. So not just 12 AMUs. If you see a carbon, it's how many carbons are there. So if you look down below, voila, 6 carbons, each weighs 12. 12 hydrogens, each weighs 1. 6 oxygen, each weighs 16. Do the math, we get a number 180. Everybody agree with me? Everybody follow me on that? That's how you calculate molecular mass. All right, now here's what Avogadro said. I read about why he was able to say this, and I kind of understood it, but I don't want to confuse you with it. You can look online and see why this is the way it is. In the case of glucose, if someone said to you, hey, Steve, go on into the lab and get me 1 mole of glucose. So whoever's told me this, they want me to go in the lab and get them 6.02 times 10 to the 23rd molecules of glucose, right? That big long number, that's how much they want me to get. How much do I do? Well, I go into the lab and I measure out 180 grams. Where did the 180 come from? Right there. I summed up the molecular mass. So 180 grams of glucose has that many molecules, has Avogadro's number, that big number. And that is, by definition, 1 mole of glucose. Everybody good with me? Didn't lose anybody? Let's try a couple of examples. Let's do a simple one first. Water. How many grams is 1 mole of water? If you've forgotten the formula for water. Hold on. There you go. Tim, how'd you get that number? Okay. So the 1 plus 1 are the atomic masses of the 2 hydrogens, right? And then the 16 is the atomic mass of oxygen, isn't it? So you added those up, and you got 18. And 18, if I tell you in lab tomorrow, hey, go get me 1 mole of water, you're going to go get me 18 grams of water. Okay, what if I said, okay, the multiplication comes in because it's the number of atoms, like in CO2, all right? Calculate CO2. Let's do it piece by piece. What's the atomic mass contribution of carbon? How much does a carbon atom weigh? Okay, it weighs 12. And how many carbon atoms are there? Just 1, okay? So 12 times 1, which, you can write, but you understand, of course, that's 12, right? Oxygen. What's the atomic mass of an right? There you go. So 32. What did you say, Tim? Did I screw up or did you screw up? 44, 32. It's 34, isn't it? Oh, no, gosh. Stop. Don't think what I just said. Yes, it's 32 there and 12. Thank you, Tim. It is 44. Tim is correct. Oh, numbers. Anybody confused? Any questions on that? So if I gave you a moles problem to do on your lab exam or your lecture exam, I would give you the formula. Okay, this is what we call the empirical formula of whatever I'm asking you to calculate. And I would give you the atomic masses. The only thing you got to remember is that right there. And you got to remember that in the end, what's that number mean? 180. 180 what? 180 grams of glucose, 44 grams of carbon dioxide, 18 grams of water is a mole. Any questions? If you ever see moles again in chemistry class, that's how you do it. Now, again, in chemistry, they can talk to you about why that is, that magic, I guess, at this point. That's why I used to tell my kids when they were younger, right? How's that work, Dad? I'm like, oh, I don't have time to tell you about that. It's magic. Not 44, and it's not in the water yet. Don't look at what molarity means for a second. So it's glucose, not 44. Carbon dioxide is 44. Is that what you meant? Yeah. So carbon dioxide is 44. So 44 grams of carbon dioxide is a mole. 180 grams of glucose is a mole. So essentially, that's what you get. Whenever you do this calculation, that number you get tells you how many grams of whatever you're talking about has that much in it, has that many molecules. Are we all good with that? Yes. Thank you, Tim. That's right. Because look down below what Tim just noticed about molarity. Molarity, which is similar to the word mole. Now, again, so you understand when you see it again, mole, the unit of mole is MOL, up above, little MOL. Molarity is capital M. Now, molarity is make me a 1 molar substance, and make me a 1 molar solution of glucose. Okay, remember the 180 grams of glucose that you measured out for me? Or the 44 gram carbon dioxide, or what was it, 18 for water? Whatever that is, take that many grams, put it into 1 liter of water, and you now have a 1 molar solution. Right? As Tim says, molarity is a ratio. How many moles do you have in 1 liter of water? So to make a 1 molarity solution of carbon dioxide, 44 grams of carbon dioxide, 1 mole of water. To make a 1 mole solution of glucose, 180 grams of glucose, 1 mole of water. Or excuse me, 1 liter of water. Cool. Everybody good with that? Okay, Raymond, what? Tell me where, so the calculation of what a mole is that it, or the molarity aspect? Okay, molarity is just another a measurement in this realm. A mole is how many molecules you have. A molarity is that number of molecules, that big number up the top, in 1 liter of water. Think about measurements in general are just things we define. We say a pound weighs this, a kilogram weighs this. We're saying in the lab, us scientists, if you put 180 grams, if you put a mole of something into a liter of water, you have a 1 molar solution. So it's just a definition of a unit. Like telling somebody how long a yard is. Cool. All right. Now, remember I was saying how you could put India ink into water and see it bounce around? Like there's a lot going on behind the scenes with molecules than we think about. I think that's kind of fascinating too. But the next slide is going to kind of give you an example of one of these behind the scenes things that's happening that you never even really think about it because it doesn't affect you necessarily. Sometimes when water molecules are all together, what happens is because of, if you could think about the van der Waals forces that I was telling you about, the electrons moving around. Now, without getting really into too detail, what we can say is sometimes the oxygen in of one water molecule, let's say on the left, for whatever reason, for one thing, the hydrogen electrons are at that end, so that's going to make it a little bit negative. Maybe all of the oxygen electrons, because the way they spin around, maybe they're all at that end of the water molecule too. Maybe all the electrons, the ones from the oxygen and the couple from the hydrogen, remember van der Waals, are just spinning it around and happen to be in one spot. So what that means is the negativity of that oxygen atom, right, that's in that water molecule, for a moment, remember van der Waals changes as soon as as the electrons move, is a little more negative than normal. So maybe just enough negative that it's strong enough to pull a hydrogen off of the other water molecule. Now, it's strong, but not completely strong enough. So when I said it pulls a hydrogen atom off, I was a little bit wrong. It doesn't pull a hydrogen atom off. It pulls the proton off. It leaves the electron behind. The oxygen in the second water molecule says, oh, no, 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 no. You might be able to pull the positive away from the negative, but you're not going to pull those negatives away from my nucleus. So you can have the proton. So what basically moves between those two in that equation up at the top, notice the arrows too, right? Those arrows are equal, pointing in both directions. That means these reactions that you're seeing, if you looked at a glass of water, occur in equilibrium, back and forth. For every water molecule that's being turned into a hydronium ion and a hydroxide ion, there's two of these ions combining together, making a water molecule, back and forth. I think they say in a liter of water, like 5 million water molecules are doing this at any one time. And even though that sounds like a big number, there's a boatload of water molecules in a liter of water. All right, so it's a small percentage of the water molecules that are doing this. This tearing apart and parts of the atom being moved from one to the other is known generally as something we call dissociation. It's not such a weird word, though, right? It's the opposite of association. So the water molecules are being dissociated. They're pulling each other apart. Little tiny amounts, okay? Just few water molecules are doing this. No effect on us whatsoever. No big deal. Now, this is what's really happening. Well, water molecules are being torn apart. Protons are being moved. You see, when this oxygen here pulls at this hydrogen, it only pulls the proton off. Hydrogen is a proton and electron. The electron, there it is left behind. Okay? The reason why it was important for me that you understand that it's the proton that's moving is because protons moving and protons being important in physiological reactions is going to become very pertinent here in the next couple of semesters, or next couple of chapters. Let me make sure we define proton again. This is a hydrogen atom, right? Come on. Atomic number 1. It's got 1 proton and 1 electron. When I remove its electron, which I've done in that reaction, all I'm left with is the proton. So hydrogen atoms are unique. Among all the elements out there, all you have to do to a hydrogen atom to turn it into a proton, a subatomic particle, is take away 1 electron. You remember sodium with chlorine? Sodium lost an electron, didn't it? Sodium was the electron donor. But it wasn't just a proton then, was it? It still had 10 electrons. So that's unique among hydrogen, isn't it? So it's the protons that are being moved. Does that make sense, Raymond? Okay, now, that's what's happening, what I just circled up above. That's really what's happening. Typically, you're going to see it written like this. You're going to say that water molecules dissociate into a proton and a hydroxide ion. Basically, this is an easy way of looking at it, especially for what I'm getting ready to define over the next couple of slides. But basically, if you think about it, this is kind of what the intermediate part is. As the oxygen tears off that hydrogen proton, right, that hydrogen atom's proton, for a moment, that proton is free between the two. And then it immediately sticks to the one on the left and becomes a hydronium ion, H3O+. So that's kind of what that's doing. And the reason why you're kind of thinking about that equation as being in between before the hydrogen ion sticks to the other water is because it's the proton again that becomes important. That's why we're focusing on that. So you understand up at the top is what's really happening chemically. Down below is a shorthand for that. Make sense? Cool. Now, back onto the proton again. We have a definition in chemistry. You've heard it before. You've heard of acids and bases. Give me an example of a couple of acids. Maybe some used in a lab before, some used around the house. Sulfuric, yeah, that's a good one. Ate a hole in the bottom of my pants one time when I was sitting on a lab table. Never do that. Bleach is a base. Muriatic is acid. Muriatic, I think, actually is sulfuric, if I remember correctly. How about some acids that you might use around the house, say in the kitchen? Soap is a base, I believe. Yeah. Vinegar is an acid. There you go. Citric, yep. No, you're fine. You had the right idea because you understood that one of the things that acids do is that they dissolve things, okay? But before we, we don't talk about how acids go about doing like that, how bleaches dissolve things. Again, that's a chemistry thing. But the reason why I want you guys to think about those acids, and Raymond did mention a base, okay? Bleach is a base, for example, is there's a precise definition for what makes an acid. An acid and a base is a base. It's very simple. It's no more difficult than this. Yeah, citric acid in orange juice is an acid. Unless you're talking about the ex-football player that murdered his wife. It's all about the protons, folks. The definition for acid. Someone walks up on the street. Hey, what's an acid? This is what an acid is. An acid is anything that when you dissolve it in water, there you go. Anything that when you dissolve it in water, it donates protons. Okay, donate, what do you mean? Okay, what I'm saying is if I took hydrochloric, now we know hydrochloric is hydrochloric acid, little clear stuff in a dropper bottle, right? It's a liquid. It's not a liquid. The liquid, it's, guess what? You did the molarity thing. The liquid is because you dissolved hydrochloric in water. That's why maybe in chemistry class sometimes you'll see a 1 molar hydrochloric or you'll see a 1 molar sulfuric. You can now figure out how much sulfuric or hydrochloric was put into a liter of water. HCl, Cl is 17, H is 1, 18 grams. 18 grams in a liter. They made a 1 molar of hydrochloric acid. Okay? So that's not the acid. What happens when you put hydrochloric into water, when you take the moles and put it into water to make the molarity thing that I'm talking about, is that substance, the HCl, dissociates. Notice the arrow in this case only goes one direction. So what we're saying is when you put HCl into water, what HCl does is it dissociates, the water molecules start tearing it apart, and what it does is it donates, excuse me, I don't want to say creates, because it didn't create the hydrogen ions, but what it does is it dissociates into two parts, basically. Some other part can be anything but a proton. Proton, all of them, all acids donate protons. All acids, when you dissolve them in water, break apart and give you a proton. They're proton donors. That's what acids are. Vinegar does it, citric does it, sulfuric does it, hydrochloric does it, all of those things. Sulfuric is the second one down below, by the way, H2SO4. Timmy was a chemist. No, sorry, don't need Tim. It's just the word. Tim was a chemist, and now he is no more for what he thought was H2 or H2O was H2SO4. Is that awful? Again, Tim, didn't mean to pick on you. You probably know the difference between H2SO4 and H2O. But they're acids, okay? That's what acids do. It's kind of like the Geico commercial. All right. So, if you look at some chemistry book and you see some chemical reaction and it's got an H and it's got X, there's no element X, but it's something. And the result of that chemical reaction is a proton. Now, there's another word for a proton, by the way, and I'll use them interchangeably so you're not confused. That's also a hydrogen ion, isn't it? It's a cation. It's a hydrogen ion. And then whatever the X is, and that's going to be where the negative charge is, if you see that right there, acid, boom, 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 acid. That's why we say the general formula for acids is just that, HX. Okay. Makes sense, right? All right, now, let's take a look at bases. H2O2. Yeah, Tim, they don't. Those are really what we call hydrochloric and sulfuric are very strong acids. Peroxide is H2O2. It does the dissolving part, if you will, works because it's not an acid or a base. It's a heavy oxidizer. Remember, we talked about that the other day, right? That's why it's good for blood. It can oxidize blood really well, and it cleans stuff out. Yeah, that's how it works. It creates these things called free radicals, which are really bad and tear things apart. You might have heard about it in terms of health concerns. Free radicals are disruptive. And peroxide makes a bunch of those, and that's what kills. That's why it's a good antibiotic. It's also good for taking meat off the bone. When killer whale used to die at SeaWorld, that's what we did. We would cut as much of the meat off as we could, and then we would take the parts and put them into big waste buckets with 30% peroxide, hydrogen peroxide. We use this stuff in the laboratory. If you use it, or the stuff you buy at the store is 3%, and we would let them sit for about 6 months. Is that right? I haven't seen it, but is that what he does? It's effective, man. Yeah, about 6 months, you pull that stuff on there, all it would be this liquid mush at the bottom, which was all the rest of the skin and the blubber and all that, and skeleton. That was it, man. Okay, enough getting us ready for breakfast. Let's talk about a base. A base is the opposite of an acid. Okay, it's something that absorbs protons. Right? So it's not a proton donator. That's an acid. It's a proton acceptor. Look at the second example first. That'll make more sense. Ammonia, NH3, is a proton acceptor. It's a base. And what it does is it'll take a proton and it'll make a an ammonium ion. That's what that's called. It's an ammonium ion. All right. Now notice, Tim, notice those reactions do go either way. So, again, it's the strength of the base. Ammonia is a pretty strong base if you poured it in your eyes, but chemically speaking, it's not one of the stronger bases. But nonetheless, it's doing the same thing. It's absorbing those protons, doing exactly what it says. Okay, now, the reason why I wanted you to look at that one second, ammonium bath salts, right? Ammonium something or other. Sulfate, right? Ammonium sulfate, I think is what they use. Yeah. And you can see why it works. It's kind of a mild base. Tim, how strong it holds it once it... what do you mean? What do you mean by that? You talking about the ammonium? Yeah, the stronger an acid or the stronger a base is, what we mean by that in strength is some acids donate protons more easily than others or more completely than others. Like hydrochloric gets them all. Sulfuric, get them all. NH3 is a weaker base, and so it absorbs some protons and then it lets them go. So it still does the base thing, absorbing protons. It's just not quite as strong, right? That's why the arrows are going both ways. Now, notice up above, NaOH, that's a strong base. Notice the arrow only goes one way, right? Now, if you're confused as to why that's a proton absorber, NaOH, because there's no indication that protons were absorbed there, I got to remind you that NaOH comes in little pellets. Again, you see it in a dropper bottle as a liquid. You think it's a liquid. It's not. It's been dissolved in water. And I got to remind you that in water, this is happening, this part here, right? The top part is happening too. But in that water that the sodium hydroxide is being dissolved in, the water molecules are also doing this. The water molecules are making hydrogen ions and hydroxide ions, and it's in equilibrium. Remember, for every water molecule falling apart, a pair of these ions are sticking together. Everything's nice and normal. Now, throw in the NaOH. So let's do that here. Let's put in sodium hydroxide, a very strong base. Okay, it dissociates. Okay, now what the OH ion does there is it overwhelms all of those protons that water molecules are giving up anyway. So the excess OHs, why are you saying excess? Well, there's an OH from the NaOH. There's an OH when a water molecule falls apart. These two things overwhelm the protons, and so they suck them up very quickly. So the reason why NaOH is a base is because it itself doesn't absorb the protons, but when it dissociates, this thing absorbs the protons, right? So this goes on and grabs a proton and then makes water. But whatever it makes, it's absorbing protons, and that's what makes it a base. That's why both of these things, even though they do it differently, both of those are considered bases. Make sense? All right. Proton donators are acids. Proton acceptors or absorbers are bases. Okay. Now, that brings us to this next thing, the pH scale. You may have worked with the pH scale before. You might be familiar with it. If not, no big deal, because we're going to go ahead and start right at the very basics. The pH scale is a scale that tells us how strong an acid or a base is. It also tells us whether something is an acid or a base, or if something's neither, if something's neutral. You can see the scale over there. If you look at the top part of the scale, the one that's in red, those are acids. Battery, some of you mentioned these. Vinegar, lemon juice, citric. Look at gastric juice. That's stomach juice, right? Tomato juice, beer, black coffee. Now, notice the arrow too. It says the increasingly acidic. So as you move from neutral pH, which you see there at 7, as you go towards the acidic side, less than 7, the further you get away from 7, the stronger the acid. So battery acid is a stronger acid than gastric juice. Gastric juice is a stronger acid than vinegar, etc., and etc., okay? The same thing works on the other side. There you go. Lye is down around household bleach. That's a very, very strong base. But the same thing works over there too. The further you get away from neutral, the stronger the base becomes. So oven cleaners are a stronger base than ammonia, a stronger base than milk of magnesia. Something that has neutral pH is neither an acid nor a base. The only thing that really neutral pH in this thing is pure water. Human blood and tears are a little bit basic. Pure water is neutral pH. It's not an acid, it's not a base. The reason why is, take a look at this. Look at the one down below again. If that's the only thing you've got in there is pure water, then this is happening in equilibrium. Nobody's donating protons, excess protons. Nobody's absorbing excessive protons. Protons have a partner. Each proton has a hydroxide ion. This equation is going back and forth. Seesaw is very nice and balanced. We're all in homeostasis. No big deal. Right? Neutral pH. All right. Now look at what goes on as you become increasingly acidic. Look what's written onto the sides. When we put a bracket around something in chemistry, that shorthand means concentration of. So I just wrote the concentration of CO2. That's what brackets mean. Notice what it says in those brackets. Take a look at it for just a second. It's an H plus in a bracket greater than an OH minus in a bracket. You see that? Now translated, what that's telling you is as it becomes more acidic, then the solution is donating more protons. Okay, it's donating more and more and more protons. So what chemically makes battery acid a stronger acid than urine, oh, that's a good one, is because battery acid, when you put it in solution, that material, battery acid is sulfuric, by the way, when it dissociates, it gives up lots of protons, battery acid does. Urine gives up some protons. Battery acid gives up a lot more. Those numbers that you see there, 1, 2, 3, 4, actually do mean something. Right? They mean something in terms of concentration. I don't know. Give me an example when you would use yogurt to neutralize something. Maybe I can. Is this the, oh gosh. Did you read the story about the woman who heard about eating yogurt would help deal with yeast infections? But she misunderstood it to mean that the yogurt needed to be applied topically. Right? You didn't realize eating it. Yeah, that's exactly what it's called. True. Yeah. Yogurt doesn't neutralize the yeast. Yogurt has a lot of good bacteria. Yeast is an opportunistic invader. In other words, yeast will invade nice, warm, moist places if there is an opportunity. If you, for example, if a female is taking antibiotics, if you've taken them for any length of time, you know usually after antibiotic treatment you get a yeast infection, don't you? The reason being is those antibiotics killed off the bad bacteria, but since they're broad spectrum, they kill off all bacteria. So unfortunately, a lot of the bacteria in our bodies are good bacteria, and down in those areas that you find yeast infections, there's a lot of good bacteria too. Now, good bacteria could mean they're beneficial, right? Or they just take up space. If that bacteria is not harming you, if it's not helping you, it might be helping you because it consumes resources. Okay, I'll let you think about what those might be, but it also takes up space. If you kill off those bacteria, it's kind of like when we talked about evolution. If you kill off those bacteria with the antibiotic, then guess what? Yeast goes, there's nobody here. I got plenty to eat. I got plenty to grow. And that's how that happens. So yogurt actually provides the good bacteria, which number one could either help destroy the yeast or just simply take up space. So the yeast can't be opportunistic. But yes, you eat it. You don't slop it in your drawers. I can't imagine walking around all day with yogurt in my drawers and not realizing why. I must have read the instructions wrong. Right? I hope she didn't get fruit at the bottom. That would have been really bad. Okay, you see the little beakers over there on the far left-hand side? They're giving you a good idea, a good visual representation about what physically is happening here. As something is acidic, it has a lot more protons than it's got those OH ones, those hydroxide ions. See, I put them in red there. And as something becomes more and more acidic, that means there's more and more of those protons. It's about the protons again, folks. Notice at the neutral pH, the protons, the red equal the black. That's why it's not an acid or a base. But then in the basic, it's the other way around, right? So there's a lot of those OHs, which could have come from sodium hydroxide, that are absorbing those protons. Now, the only way you might change the basic solution down below could also be ammonia doing that, right? Could be an NH3. Whatever it is, there ain't a lot of protons. You guys understand it's all about the protons? Any questions on that? More and more and more and more protons, the stronger the acidic, or the stronger the acid, less and less and less protons, the stronger the base. See, the scale works the other way on the other side. See here? Less protons in the OH. No, OH are a group of atoms right there. It's the oxygen and the hydrogen with the electron that was left behind. So water gives you a hydroxide ion, so does that one. And of course, remember what I said, what happens, it's like a two-step operation with this one, because then the protons that are already there from the water, there's a lot of OHs, starts removing those protons, starts lowering the number of protons, and we get a basic solution. Something that removes a lot of protons is very basic. Oven cleaner, that's nasty stuff, man. Oven cleaner removes lots of protons. Now, again, I haven't gotten into the reason as to why these things dissolve stuff. That's a chemical thing. It's more of a definition and just kind of an introduction here. You guys got any questions about the protons? Because the next thing I have to say has to do with protons, and I want to make sure everybody's on the same page with that before we go on. Where are we? Oh, good. Perfect time. All right. Little p, big H. That's how we write pH. Little p, big H. If something has a pH of 4, we indicate it that way. There's a reason why it's a little p and a big H. It has to do with known as an exponential or a logarithmic equation. That's what's up in the upper red box in the upper side. Technically defined. Now, if you haven't had math or math's not your long suit, don't lose me here. It's going to start off complicated. It might even get a little more, and then it's going to get easy. So stick with me. This is how we define pH. We take the concentration of protons, H pluses, hydrogen ions. We measure that. It's not going to be very many. It's going to be a really small number, 1 in a bazillion, but whatever the case may be. And we take the log of that. That's that little thing on your calculator. You hit log, and it gives you a numbers. And then we take the negative of that. That's how you calculate pH. All right? Make sense? Okay, so let me give you an example. Let's take a neutral solution. A neutral aqueous solution. Let's take pure water. Pure water has a pH of 7. Let's figure out how we did that. If we counted up the number of protons in pure water, we would find there are 10 to the minus 7. Now, what does that mean when we see a number 10 to the minus 7? How would we write that out longhand? Did you get the same one as me, Tim? 6 zeros? Yeah, that's what that means, right? You're going to move the decimal point to the right 7 places. Okay, I'm having you guys take a look at that. Now, that is a number. Tens, 100,000, 10,000, 100,000, millions, 7 10 millionths. All right, so what we're saying in that water, the concentration of protons is 7 10 millionths. So for every 10 million water molecules, there are 7 protons. Not very many. Now, what you see down below is how we calculate the pH. You take that concentration, 10 to the minus 7, you take the log of that, that gives you minus 7. You take the inverse of that, you get 7. Remember how I did with the metric system? Let's make it real easy here, folks. It's simple as dirt to figure out the proton concentration or what the pH of something is. Something that has a proton concentration of 10 to the minus 11 has a pH of what? Something has a pH of 10 to the minus 1 has a pH of what? Ladies? Josh? Tim? Take a chance. Take a chance. Look up here, right? Look at Tim's answer. So 10 to the minus 1. Hey, Raymond, hold on 1 second. I'm asking you to calculate a pH number based on a proton concentration. This is a proton concentration. 0.01 protons, 10, 100. That's 1 proton for every 100 water molecules. It's a concentration. That's what it is. What I'm asking you is take that concentration and give me a pH from it. You can put it into your calculator, take the log, and take the minus of that and get the answer. Okay? But if I ask you for pH and I give you the proton concentration, 10 to the minus 3. All right? What's the pH of a solution that is 10 to the minus 3 proton concentration? pH 3. Whatever the exponent is, 10 to the minus, here you go. What's the pH of that? X. The pH, the numbers that you see on the pH scale, not the concentration. You got to work between the concentration the other way around. Okay, now, keeping that in mind, let me erase this for a second. What if I said, all right, something has a pH of 9. What is its hydrogen ion concentration? 10 to the minus 9. There you go. Okay, now, just so you know, pH scale can also have divisions in between. Doesn't have to be even. So what if something has a hydrogen ion concentration of that? What's its pH? .3. I'm sorry, 2 point, yeah. Beth and Lindsay, you saw that as 2 times 3. Sorry, that's minus 2.3. Yeah, there you go. Okay, so all of this log, take the opposite of all that. Now, you go on chemistry class, you'll have to learn how to do that because it's calculations. But I wanted to, cut to the chase right here because I'm not expecting you to do the calculations, but I might want you to recognize the relationship between pH and proton concentration. It's very simple, though. It's the exponent. All right, if I give you the pH and tell me what the proton concentration is, that's the 10 to the exponent, okay? And if I give you the proton concentration, then the exponent is the pH. Any questions on that? Cool. And if you want to play with it, put it in your calculator. Take 7, take the log of that, take the minus of that, and you'll get the answer 7. Okay, good. I got 4 more minutes to finish the last part. It fits very nicely in with here, and that'll be a good place to stop. Remember again tomorrow, folks, to bring lab 2, closed-toed shoes, and all that sort of stuff. Okay? All right. Let's talk about buffers for just a second. Buffers have to do with this characteristic of life we've discussed a million times already in the couple of weeks we've been together, and that's homeostasis. A buffer is a substance that stabilizes or maintains pH. All right, so it maintains the acidity or the basicity of something, of an environment. What I mean by that is you could put a buffer into a beaker and it would do its job. We have buffers in our body. We have substances that in our body, what they do is they regulate pH. Some parts of our body are pretty acidic. The stomach, right? Gastric juice had a pH of 2. That's why when you rift up, like maybe after Taco Bell, right? You go, oh my God, that burns. Yes, that's acid that's burning your esophagus, right? Some parts of our body, like down in our intestines, are a lot more basic. Everything is balanced. Too hot, you sweat. Too cold, you shiver. Too acidic, you got to fix that. You got to make it back more towards the basic side. Too basic, got to be too acidic, right? You got to move it towards the acidic side. Got to keep everything in balance. That's what a buffer does. A buffer is a substance, a chemical substance that does that. For example, in your blood, you have a buffer known as carbonic acid. And you're going, wait a minute, I thought buffers buffer acids. Well, yes, acids can buffer things, all right? Let's see how that works. First thing I want to talk to you about, though, is where the carbonic acid comes from, because it's important for me, again, to always be able to kind of trace back. All right, we're in your bloodstream. You have water in your bloodstream. Where does the carbon dioxide in your bloodstream come from? Yeah, right? It's a byproduct of respiration. Now, a lot of that you give off in your lungs. You exhale carbon dioxide, but not all of it. Some of it combines together and makes something called carbonic acid. Now, don't worry about carbonic acid being in your blood. Carbonic acid is very, very, very weak, a very weak acid, very, very weak acid, okay? Here's how carbonic acid works as a buffer, though. Let's take a look on the far panel. Let's do this with a couple of scenarios first. Let's imagine for some reason your blood is becoming too acidic. Okay, for some physiological problem, your blood is becoming too acidic. All right, so tell me chemically what's happening in your blood. It's becoming too acidic because it's getting too many of what in it? What do acids put into solutions? Protons. I'm going to guess that's what that means. Yep, protons, right? H+, hydrogen ions, right? That's what acids do. So now look at that panel on the right-hand side. Do you see the hydrogen ion? Right? So your blood's becoming too acidic. Something's happening to your blood. Oh no, alert, alert, alert. There's too many protons in my blood. There's too many hydrogen ions. The carbonic acid says, I'll take care of it, sir. It dissociates, okay? And it makes these bicarbonate ions. Now these bicarbonate ions start absorbing those protons. Okay? They start absorbing those protons, and then you think, well, doesn't that just make carbonic acid? Well, then the carbonic acid starts falling apart into water and carbon dioxide. You give the carbon dioxide when you exhale. Ergo, step 1, step 2, step 3, you get rid of protons. Does that make sense? You see how that works? Too many protons means lots of bicarbonate ions are going to stick to those protons, make carbonic acid. Reactions work kind of like the teeter-totter again. If this right here gets really high in concentration, that's going to force the reaction into this direction. So you got a high concentration of protons, that's forcing this reaction that way. You're making a lot of carbonic acid, That's forcing this reaction this way, and you're giving off a lot of carbon dioxide, so it's getting rid of those protons. See? All right, now, does that make sense to everybody? I know I'm running in time. I got one more question. I'll leave you alone. Does that make sense how that works? Actually, that's the next to last question. Now, your blood becomes too basic. Your blood becomes too basic. What happens to the number of protons in a base? Does it go up or go down? In a base. Goes down. There's not enough. Alert, alert, alert. There's not enough protons. Remember before there were too many? Now it's the other way. Alert, alert, there's not enough protons. This is getting low, these protons here. We've got to do something about that. Why? Because we have to maintain homeostasis, folks. But carbonic acid says, I'll save the day. So carbonic acid starts dissociating. And guess what? Carbonic acid is an acid. So it donates protons. See how isn't this beautiful? This is part of that old balance that I'm talking about. Heck yeah. And there's all kinds of buffers out there, which we'll talk more about. All right. Sorry, folks. I ran a couple of minutes over. That's all I got for today. I'll see you guys in class tomorrow. Lab number 2. We'll continue on. Actually, we're done with this chapter. We're going to chapter 4. Oh, cool. Carbon. I love talking about carbon. All right, Zach, you take care. See you tomorrow, Tim.